I took the code that we developed in this Jupyter notebook and I converted it to be a script. And I'm doing this because I just want to simplify our intermediate work into just the final product that we have at this point. So in the top here, I put all the hyperparameters that we've defined. I introduced a few, and I'm going to speak to that in a little bit. Otherwise, a lot of this should be recognizable. Reproducibility, read data, get the encoder and the decoder, create the train and test splits, use the kind of like data loader that gets a batch of the inputs and targets. This is new, and I'll talk about it in a second. Now this is the bigram language model that we developed, and it can forward and give us a logits and loss, and it can generate. And then here we are creating the optimizer, and this is the training loop. So everything here should look pretty familiar. Now, some of the small things that I added. Number one, I added the ability to run on a GPU if you have it. So if you have a GPU, then this will use CUDA instead of just CPU, and everything will be a lot more faster. Now, when device becomes CUDA, then we need to make sure that when we load the data, we move it to device. When we create the model, we want to move the model parameters to device. So as an example, here we have the NN embedding table, and it's got a .weight inside it, which stores the sort of lookup table. So that would be moved to the GPU so that all the calculations here happen on the GPU and they can be a lot faster. And then finally here, when I'm creating the context that feeds into generate, I have to make sure that I create it on the device. Number two, what I introduced is the fact that here in the training loop, here I was just printing the loss.item inside the training loop. But this is a very noisy measurement of the current loss because every batch will be more or less lucky. And so what I want to do usually is I have an estimate loss function, and the estimate loss basically then goes up here, and it averages up the loss over multiple batches. So in particular, we're going to iterate eval iter times, and we're going to basically get our loss, and then we're going to get the average loss for both splits. And so this will be a lot less noisy. So here, when we call the estimate loss, we're going to report the pretty accurate train and validation loss. Now, when we come back up, you'll notice a few things here. I'm setting the model to evaluation phase, and down here, I'm resetting it back to training phase. Now, right now for our model as is, this doesn't actually do anything, because the only thing inside this model is this nn.embedding, and this network would behave the same in both evaluation mode and training mode. We have no dropout layers, we have no batch norm layers, etc. But it is a good practice to think through what mode your neural network is in, because some layers will have different behavior at inference time or training time. And there's also this context manager, torch.nograd, and this is just telling PyTorch that everything that happens inside this function, we will not call .backward on. And so PyTorch can be a lot more efficient with its memory use because it doesn't have to store all the intermediate variables because we're never going to call backward. And so it can be a lot more memory efficient in that way. So also a good practice to tell PyTorch when we don't intend to do backpropagation. So right now, this script is about 120 lines of code and that's kind of our starter code. I'm calling it bigram.py, and I'm going to release it later. Now, running this script gives us output in the terminal, and it looks something like this. It basically, as I ran this code, it was giving me the train loss and the val loss, and we see that we convert to somewhere around 2.5 with the bigram model. And then here's the sample that we produced at the end. And so we have everything packaged up in the script, and we're in a good position now to iterate on this. Okay, so we are almost ready to start writing our very first self-attention block for processing these tokens. Now, before we actually get there, I want to get you used to a mathematical trick that is used in the self-attention inside a transformer, and is really just like at the heart of an efficient implementation of self-attention. And so I want to work with this toy example to just get you used to this operation, and then it's going to make it much more clear once we actually get to it in the script again. So let's create a b by t by c, where b, t, and c are just 4, 8, and 2 in this toy example. And these are basically channels, and we have batches, and we have the time component, and we have some information at each point in the sequence, so c. Now, what we would like to do is we would like these tokens. So we have up to 8 tokens here in a batch. And these 8 tokens are currently not talking to each other, and we would like them to talk to each other. We'd like to couple them. And in particular, we want to couple them in a very specific way. So the token, for example, at the 5th location, it should not communicate with tokens in the 6th, 7th, and 8th location, because those are future tokens in the sequence. The token on the 5th location should only talk to the one in the 4th, 3rd, 2nd, and 1st. So information only flows from previous context to the current time step. And we cannot get any information from the future because we are about to try to predict the future. So what is the easiest way for tokens to communicate? Okay, the easiest way I would say is, okay, if we're a 5th token and I'd like to communicate with my past, the simplest way we can do that is to just do an average of all the preceding elements. So for example, if I'm the 5th token, I would like to take the channels that make up that are information at my step, but then also the channels from the 4th step, 3rd step, 2nd step, and the 1st step. I'd like to average those up, and then that would become sort of like a feature vector that summarizes me in the context of my history. Now, of course, just doing a sum or like an average is an extremely weak form of interaction. Like, this communication is extremely lossy. We've lost a ton of information about the spatial arrangements of all those tokens, but that's okay for now. We'll see how we can bring that information back later. For now, what we would like to do is, for every single batch element independently, for every teeth token in that sequence, we'd like to now calculate the average of all the vectors in all the previous tokens and also at this token. So let's write that out. I have a small snippet here, and instead of just fumbling around, let me just copy paste it and talk to it. So in other words, we're going to create X, and BOW is short for bag of words, because bag of words is kind of like a term that people use when you are just averaging up things. So this is just a bag of words. Basically, there's a word stored on every one of these 8 locations, and we're doing a bag of words, so just averaging. So in the beginning, we're going to say that it's just initialized at 0, and then I'm doing a for loop here, so we're not being efficient yet. That's coming. But for now, we're just iterating over all the batch dimensions independently, iterating over time, and then the previous tokens are at this batch dimension, and then everything up to and including the teeth token. Okay? So when we slice out X in this way, xprev becomes of shape how many T elements there were in the past, and then of course C, so all the 2-dimensional information from these little tokens. So that's the previous sort of chunk of tokens from my current sequence. And then I'm just doing the average, or the mean, over the 0th dimension. So I'm averaging out the time here. And I'm just going to get a little C 1-dimensional vector, which I'm going to store in X bag of words. So I can run this, and this is not going to be very informative because, let's see, so this is X of 0, so this is the 0th batch element, and then expo at 0. Now, you see how at the first location here, you see that the 2 are equal, and that's because it's we're just doing an average of this 1 token. But here, this one is now an average of these 2. And now this one is an average of these 3, and so on. So, and this last one is the average of all of these elements. So vertical average, just averaging up all the tokens, now gives this outcome here. So this is all well and good, but this is very inefficient. Now the trick is that we can be very, very efficient about doing this using matrix multiplication. So that's the mathematical trick. And let me show you what I mean. Let's work with the toy example here. Let me run it and I'll explain. I have a simple matrix here that is a 3 by 3 of all ones, a matrix B of just random numbers, and it's a 3 by 2, and a matrix C, which will be 3 by 3 multiplied 3 by 2, which will give out a 3 by 2. So here we're just using matrix multiplication. So A multiply B gives us C. Okay, so how are these numbers in C achieved, right? So this number in the top left is the first row of A dot product with the first column of B. And since all the row of A right now is all just ones, then the dot product here with this column of B is just going to do a sum of this column. So 2 plus 6 plus 6 is 14. The element here in the output of C is also the first column here, the first row of A, multiplied now with the second column of B. So 7 plus 4 plus 5 is 16. Now you see that there's repeating elements here. So this 14 again is because this row is again all ones, and it's multiplying the first column of B. So we get 14. And this one is, and so on. So this last number here is the last row, dot product, last column. Now the trick here is the following. This is just a boring number of, it's just a boring array of all ones, but Torch has this function called trill, which is short for a triangular, something like that. And you can wrap it in Torch.once, and it will just return the lower triangular portion of this. Okay. So now it will basically zero out these guys here. So we just get the lower triangular part. Well, what happens if we do that? So now we'll have A like this and B like this. And now what are we getting here in C? Well, what is this number? Well, this is the first row times the first column. And because this is zeros, these elements here are now ignored. So we just get a 2. And then this number here is the first row times the second column. And because these are zeros, they get ignored, and it's just 7. This 7 multiplies this 1. But look what happened here. Because this is 1 and then zeros, what ended up happening is we're just plucking out this row of B, and that's what we got. Now here, we have 1, 1, 0. So here, 1, 1, 0 dot product with these two columns will now give us 2 plus 6, which is 8, and 7 plus 4, which is 11. And because this is 1, 1, 1, we ended up with the addition of all of them. And so basically, depending on how many ones and zeros we have here, we are basically doing a sum currently of a variable number of these rows, and that gets deposited into C. So currently we're doing sums because these are ones, but we can also do average, right? And you can start to see how we could do average of the rows of B sort of in an incremental fashion. Because we don't have to, we can basically normalize these rows so that they sum to 1, and then we're going to get an average. So if we took A, and then we did A equals A divide, torch.sum in the, of A, in the 1th dimension, and then let's keep them as true. So therefore the broadcasting will work out. So if I rerun this, you see now that these rows now sum to 1. So this row is 1, this row is 0.5, 0.5 is 0, and here we get 1/3. And now when we do A multiply B, what are we getting? Here we are just getting the first row. Here now we are getting the average of the first two rows. Okay, so 2 and 6 average is 4, and 4 and 7 average is 5.5. And on the bottom here, we are now getting the average of these 3 rows. So the average of all of elements of B are now deposited here. And so you can see that by manipulating these elements of this multiplying matrix, and then multiplying it with any given matrix, we can do these averages in this incremental fashion, because we just get, and we can manipulate that based on the elements of A. Okay, so that's very convenient. So let's swing back up here and see how we can vectorize this and make it much more efficient using what we've learned. So in particular, we are going to produce an array A, but here I'm going to call it way, short for weights. But this is our A. And this is how much of every row we want to average up. And it's going to be an average because you can see that these rows sum to 1. So this is our A. And then our B in this example, of course, is X. So what's going to happen here now is that we are going to have an expo 2. And this expo 2 is going to be way multiplying Rx. So let's think this through. Way is T by T. And this is matrix multiplying in PyTorch a B by T by C. And it's giving us what shape. So PyTorch will come here and it will see that these shapes are not the same. So it will create a batch dimension here. And this is a batched matrix multiply. And so it will apply this matrix multiplication in all the batch elements in parallel and individually. And then for each batch element, there will be a t by t multiplying t by c exactly as we had below. So this will now create b by t by c, and xbo 2 will now become identical to xbo. So we can see that torch.allClose of xbo and xbo 2 should be true. Now, so this kind of like convinces us that these are in fact the same. So xbo and xbo 2, if I just print them, okay, we're not going to be able to okay, we're not going to be able to just stare it down, but well, let me try xbo basically just at the 0th element and xbo 2 at the 0th element. So just the first batch, and we should see that this and that should be identical, which they are, right? So what happened here? The trick is we were able to use batched matrix multiply to do this aggregation, really. And it's a weighted aggregation, and the weights are specified in this t by t array. And we're basically doing weighted sums. And these weighted sums are according to the weights inside here, that take on sort of this triangular form. And so that means that a token at the tth dimension will only get information from the tokens preceding it. So that's exactly what we want.